Welcome back to multivariate calculus. In this video, we're going to be talking about reparameterization, as it says in the title card above me. We've mentioned reparameterization a couple of times as we've talked about parametric curves. But a quick review, the idea is that unlike in a Cartesian equation or a curve defined by a Cartesian equation, there are generally multiple different ways of defining the same parametric equation. And I want to explore that a little bit more carefully today. So let's think about generically some function, some parametric curve defined by r of t is equal to the vector components x of t, y of t, z of t. Now, when we've talked about parametric curves in the past, I've encouraged you to think about the coordinate space and x, y, and z are the three spatial dimensions. And if you look at a point hovering about somewhere, the vector valued function is pointing towards a point in space. And if that point moves over time, then at each different time value t, the point is in a different place. The vector valued function gives you a different output to say where the point is now. The parametric curve is playing connect the dots on all of those points that the function points to as time evolves. Now, when you think about time, there are several different ways you can think about it. Right? In our everyday lives, we track time using seconds or minutes or hours or days or months or weeks or years or centuries or millennia or eons. And a change of coordinates, a change of units, a unit conversion between time is something that we can do very readily. Now, in the graphs that we've been looking at, thinking about a unit conversion between seconds and minutes isn't really going to be of all that much benefit. Right? In steps of seconds, t equals 1, 2, 3, 4, 5, we're generally already off of the space that we're graphing. Getting all the way to 60 seconds to be equal to 1 minute is just not something that we've tried to graph here. But you can think about that same idea. One example, in film, cinema is generally shot in 24 frames per second. By contrast, video meant for broadcast on television is generally shot in 30 frames per second. And so one frame is a different amount of time on a movie or on a TV show. So if I want to map t in frames of a movie to say t star in frames of a TV show, I know that t equals 24 has to map to t star equals 30. Or in other words, t should be equal to 24 over 30 times t star. And we can reduce that fraction. They're both divisible by 6. All right, so that gives us a change of coordinates based on a unit conversion. It's not one that you're all that familiar with, but it should kind of make sense. and it's one that video analysis software is very familiar with. So let's consider a specific curve here. R of t is going to be given by, let's say, t sine of t negative cosine of t. Or, using the change of coordinates, r of t star is going to be equal to 4/5 t star sine of 4/5 t star and negative cosine of 4/5 t star. And if I jump over to GeoGebra, I can try to graph both of those. All right, so here I am at GeoGebra. Let's put some labels on these axes so I can see what's going on. All right, so going into settings, x-axis, label as x, y-axis, label as y, z-axis, label as z, and then spin the axes around to get the kind of sort of mostly in the orientation that you're used to seeing. And we can try to graph. The first one was t sine of t negative cosine of t. And that gives us this curve here. If we rotate around, we can see that it's kind of corkscrewing about the x-axis. To make things a little bit confusing, GeoGebra can only handle graphing if the independent variable is labeled as t. Otherwise, it doesn't quite know what to do. To show you what I mean, notice here that I've labeled s, sine of s, cosine of s. And instead of giving me a curve, if I get rid of the first one that I graphed, you can see that it gave me just a single point. And it gave me a slider here for values of s. And it's a nice thing to look at. I can move that around, and you can see what I mean when I say that the graph of a parametric curve is following and just tracing every point that the vector valued function points towards. All right, so that's interesting, but not really all that useful to us. So let's get these out of the way. And instead, we have to use t again, but we'll use the t star. So it was 4/5 t. It was sine of 4/5 t. And it was the negative of the cosine of 4/5 t. All right. And now if I get rid of these, right, you can see that there's the new graph. And if I get rid of that one and bring the old graph back, you can see that they are, in fact, the exact same curve. Right? If I traced across this using the new parameterization, you would find that the ball was moving a little bit slower, but it's still the exact same thing. All right, so that's the idea of reparameterization. In this video, I want to try to see how we can make use of reparameterization. And for that, I am going to do a couple of things. The first thing that I want to do is focus a little bit more closely on projections, because looking at how things work in 3 dimensions is a little bit tricky. So actually, let's go back to these curves that we were graphing and look at our idea of projection. If I spin things around and look at the x and y direction, x we had t, y we had sine of t, and we have a graph that looks like sine. Obviously, it comes out of and into the plane, but when you look down on it, it is the sine wave. And this is what we're talking about when we say a projection. We're going to collapse the z dimension down to nothing and just look at the x and y. Or we could look at y and z. If I can get this lined up just right, we should get a nice circle that shows up there. Or if we look at x and z, you get a negative cosine wave, which is exactly what we said we were going to get. All right, so those ideas are called the projections, and we're going to look specifically at a projection in the xy plane. So I'm going to go away from the three-dimensional graph and into a two-dimensional graph just to make my life a little bit easier. And I'm going to look at an application in kinematics. I feel fairly confident in assuming that anyone who is taking a multivariate calculus course has already had exposure to physics and kinematics at least a basic level. If you have not, I apologize. This might go a little bit quickly, but I can at least assure you that you're not missing too much. We're looking at this as an application, as a way to think about what's going on here. So if you've not seen these equations before, I apologize, but specifically in kinematics, I'm going to be looking at projectile motion. And the equations of projectile motion say that y is equal to vy times t minus 1/2 times g times t squared, and x is equal to vx times t. Specifically, the component here, vector v with components vx, vy, is the initial velocity of our curve. And g is gravitational acceleration. Right? Gravity pulls objects on the surface of Earth downward at an acceleration of approximately 9.81 meters per second squared, which is the value that I much prefer using myself. But for specifically the application of kinematics in mathematics, it's actually advantageous to use the US customary system. I know I hate the US customary system when doing anything physics related. I'm sure that anyone who has ever studied physics hates using the US customary system for anything physics related, but it has the really nice property of the acceleration due to gravity in US customary units is 32 feet per second squared. And 32 is a nice number because it factors nicely and it lets us have problems that have really nice values showing up. So I'm going to set here that g equals 32, and we're going to be using units of feet per second squared. All right, so rewriting this then, y is equal to vy t minus half of 32 is 16 t squared, and x is vxt. So if I pick a couple of representative vectors, a representative velocity to play around with, let's say that we have an initial velocity with components Vx is going to be 7 feet per second, and Vy is going to be let's go with 20 feet per second. All right. So what we have here is an idea that we can represent physically without really thinking about it too much. I've got a cannon, and it's shooting something up, far more upward than overward, but it's going to go up for a while, it's going to reach a peak, and it's going to come back down. And if this was a course in kinematics, we would be interested in looking at some things like, well, how high does it get at its peak? Or how far across does it get before it's done? But this is not a course in kinematics, so that's not the question I'm going to be answering. Instead, I'm going to be answering questions about how can we model things. I'm going to start off by writing the vector valued function here. Again, we're projecting down into 2 dimensions. We're assuming that this projectile is just moving in the z-plane. Makes life a lot easier. And I'm going to answer 2 questions a little bit later on. Can we reparameterize so that each step of height represents an easily identified unit? And can we reparameterize so that each step of distance represents an easily understandable unit? But let's start by going into GeoGebra, into the 2-dimensional GeoGebra. That's all right, here we go. Regular 2-dimensional GeoGebra. And we had our parametric curve given by x of t was vx times t, and vx is 7. So I have here 7t as my x-coordinate, and then my y-coordinate is going to be 20t minus 16t squared. Again, vy, which is 20 times t, and then minus 16 times t squared is the acceleration. And when I graph that, I get something that looks mostly like a straight line because I am really zoomed in. So let's zoom out a bit until we can really see the shape of the parabola. Maybe move it a little bit so that it's nice and centered in our view. All right, and again, if we cared about the maximum height and about the total distance, we could get those pretty readily. That's not really what I care about. Instead, I care about reparameterization. And reparameterization is a little bit hard to follow in GeoGebra. So let's go back over to our notes and rearrange things. So again, we have r of t, which had components 7t and 20t minus 16t squared. If x is 7t, then t is x over 7. And I can get r of t of x by replacing t with x in this. So I have 7 times x over 7, which is just x. I have 20 times x over 7, which is 20 over 7 times x, and then minus 16 over 7. I'm sorry, 16 over 7 squared, which would be 16 over 49 x squared. And again, because of limitations of GeoGebra, I have to input this using t's instead of x's. But the important thing to consider here, that's not my highlighter. The important thing to consider here is that my x-coordinate is the parameter. So instead of thinking about how I'm moving along this curve in time, I'm instead asking a very different question of, at each step along the way, how far have I gone? Or every time I take a step forward, how far up or down am I? It's a different question that we're asking, but it gives us the same kinds of information. And again, it looks weird because I have to use t again, but because that x component is the parameter, that's what we're looking for. And then we had 20 over 7 times t minus 16 over 49 times t squared. And you can see that it is giving us the exact same curve. All right, that's interesting. Again, we have this nice result. If we change and solve for one of the components, we can reparameterize so that each unit is an equal step in that direction. In the x direction, it was fairly straightforward. In the y direction, it's going to be a little bit messier. So let's go back to our notes here. Let's copy this so we have some space to work. And this time, instead of solving for x, we're going to solve with y. Y is equal to 20t minus 16t squared, and that looks a little bit intimidating, but that's the same thing as 16t squared minus 20t plus y equals 0, so we can solve that using the quadratic formula. T itself is the negative of b, which is 20 in this case, plus or minus the square root of b, which is 20 squared. Negative 20 squared is 400, minus 4 times a, which is 16. 4 times 16 is 64, times y, all over 2 times a. 2 times 16 is 32. All right, so we have 20 over 32. Those are both divisible by 4, so that will reduce to 5/8. And then we have some fractions here. All right, 464 have a common factor of 8, I guess, but that's not all that useful. Does 16 work? 400 divided by 16 is 25. All right, so 16 square root of 16 is 4. And so this is going to be 32 divided by 4 is 8. 400 divided by 16 is 25. 64 divided by 16 is 4. And while those are both perfect squares, unfortunately, y is not a perfect square, and there's not really anything else we can do with that. All right, so we get a really ugly form here. But we can still use it. R of t of y is, well, the x component is going to be 7t, so that's going to be 7 times 5/8, which is 35 over 8, plus or minus 7/8 times the square root of 25 minus 4y. And then you can go through and actually plug it in if you want to, but we solve this very specifically so that the y component would just be y. Right? But here we have a problem. This is not a function. We have a plus or minus. And so when I go over to GeoGebra and I try to graph this thing, again, whoops, that's the wrong button. That's the one I was looking for. Right. Again, it's a little bit hard to see because I have to replace y with t so that this will work. But I'm going to have 35 divided by 8 plus 7/8 times the square root. And square root in GeoGebra, you can type SQRT, and then if you hit space, it puts in a square root symbol for you. There's also a nice virtual keyboard down here if you prefer finding things that way. But it was the square root of 25 minus 4 times, well, it said y, but we're writing t. And then the y component was just t. And you can see here, there's a little bit of a glow to it to make it a little bit easier to see. If I make this disappear and then come back a couple of times, we only got half of the curve by doing that. And it probably won't be too much of a surprise if I come back in here and I replace that plus sign with a minus sign, that I will get the other half of the curve. All right. But, and I apologize, I'm kind of looking over here and pointing over there because I can't see anything. This is a green screen behind me. But the idea here now is that each value of t is an equal step. T equals 0 starts here, 1, 2, 3, 4, 5, 6, and then wherever that peak was, a little bit above 6, as you find values of y, you can plug in and it will give you how far across you've gotten in order to get to that height. But the more interesting thing here is noticing that I've only got half of the curve. Right? My first reparameterization worked perfectly fine. My second reparameterization ran into some trouble. And so that's the last thing that I want to think about today, is what caused the trouble and how do we make sure we avoid it? All right, so if I come back to my notes, when does a reparameterization break the curve? And I have break in quotations here because as we saw, it didn't actually change the curve any. It's still the exact same curve we had before, but we were missing half of it. And here we can be a little bit more careful on something that I'm generally not that careful on. When you're talking about a parametric curve, you very specifically have to talk about the parametric curve for t in some interval from A to B. And that gives us right away a tool for determining when things aren't going to work. Because if my new function doesn't actually traverse in its output everything from the A to B that I care about, then the thing that I have isn't really going to work. All right, so I need to make sure that I'm getting the same kinds of outputs. All right, t of whatever it's going to be has to get me all of the values that I care about. And there are a lot of ways that that can happen that are too numerous to really quantify here. So what I'm going to look at is a sufficient but not necessary condition. That's phrasing that we've used in the past, but not all that often. Whenever my reparameterization T of S satisfies this condition, I know that the curve will be the same. That is not saying that when the reparameterization does not satisfy this condition, that the curve will not be the same, because the curve can still be the same in other conditions, but this is an easy one to find. If we set up that our function t of s is monotonic, or monotonic means either strictly increasing or strictly decreasing. I don't care which way it's going, but it's going up or it's going down. And then my endpoints get to the same places. Well, then I might be going in a circuitous route, but I'm getting there, right? Instead of going from A to B, the reparameterization might be taking me on the long route to get there, but it's still getting there, and that's what really matters. All right. So as an example, I would like you to take a look at the vector valued function r of t with components natural log of t, t, and natural log of 1 over t. And we're specifically going to be looking at the window for t between 1 and e squared. I would like you to graph this curve using GeoGebra and export 3 projections of it. So instead of just trying to find something that looks nice, give me the projection in the XY plane, the YZ plane, and the ZX plane. Then I want you to reparameterize with T of S equals e to the 1/2 S power. I want you to tell me, based on what you know about the exponential function and what I just said about reparameterizations, will this reparameterization work? If it will work, what range do we need to use for S in order to get us where we need to be? And then graph that to see that the graph actually is the same thing. All right. It feels like a lot to do, but most of it's just punching stuff into a computer, so it doesn't take all that much work. But take a couple of minutes, play around with these, see where you get to with that, and I'll see you in the next video.